Amid the endless chemical formulas flashing across the screen, one question rises above them all. What is life made of? And today, with the help of AI, humanity is not only just studying life, but actively rewriting it. From the disposal of plastics, to global warming, to cures for diseases and cancer, solutions begin to take shape, and at the heart of it lies a single key, a protein folded into the right shape. This is not a news story. The quest to understand protein structures has already reshaped science, winning Nobel Prizes, from X-ray crystallography in 1962 to the discovery of the link between sequence and function in 1972, and most recently, to AlphaFold in 2024. So, how did they do it? And how does it have the influence to solve problems outside the realm of biology? A protein starts simply as a string of amino acids. Each amino acid consists of a central carbon atom, bonded with an amine group on one side and a carboxyl group on the other. And the last thing that they are bonded to is a side chain, or an R group. At the isoelectric points, or pi, an amino acid exists as a Zwitter ion, carrying both positive and negative charges, yet balancing to a net charge of 0. Take, for example, glutamic acid with a pi of 3.2. When pH is greater than pi, the carboxyl group in the side chain is deprotonated, giving the molecule negative charges. In contrast, in lysine, pi approximates 9.7. When pH is less than pi, the amino group in the side chain is protonated, resulting in a positive charge. 1. Primary structure. The sequence of amino acids in a polypeptide chain is determined by the gene. Imagine a string of beads aligned orderly. 2. Secondary structure. The secondary structure of protein forms from hydrogen bonds within the polypeptide backbone, primarily in the form of alpha helices and beta sheets. 3. Tertiary structure. The complete three-dimensional folding of polypeptide chains stabilized by the following interactions among R groups: disulfide bridges, covalent linkages between two cysteine residues, ionic bonds, salt bridges, electrostatic interactions between oppositely charged R groups, hydrogen bonds formed between hydrogen donors and acceptors in R groups, hydrophobic interactions, nonpolar R groups clustering together in the protein core. 4. Quaternary structure. The assembly of multiple polypeptide chains into a functional complex. For example, hemoglobin consists of 4 polypeptide subunits. The power of protein resides entirely on the accuracy of its 3D structure. Folded correctly, life flourishes. Misfolding, the world turns upside down. It sounds simple, but this is precisely Levinthal's paradox that has left science astounded for years. Imagine yourself with a protein consisting of 100 amino acids, each of them having 2 rotatable bonds with 3 variations. Calculating the number of possibilities used an astounding 3 to the power of 200 unique configurations, larger than the amount of atoms in the universe. And yet, the protein can amazingly find the correct conformation in 1,000th of a second. This leaves us with a demanding question. How? How can protein be so accurate? The answer leads us to the Nobel Prize and open a new chapter in humans' history, the AI revolution. The first breakthrough came in 1951 with the publication of the helical hydrogen-bonded model of polypeptide by Linus Pauling, Corvée, and Branson. By calculating every atomic distance, every bond angle, every hydrogen bond with data from crystallography, they show that alpha helix is supple like a spring while beta sheet stretches like fabric. Only 7 years later, in 1958, the first protein structure, myoglobin, was found by John Kendrew using X-ray crystallography, confirming the earlier prediction of Pauling and his colleagues. John Kendrew was the first person to witness a protein through the lens of science. The protein myoglobin storing oxygen in fish muscles, the so-called heart of the sea, but is also jokingly referred as turd of the century by The Guardian. John Kendrew used mathematics and X-ray to execute his experiments. To begin with, protein crystals are formed by refining and concentrating the protein solution. Under the right condition, the protein molecules will arrange themselves into a small cluster, a nucleus. And as more molecules attach, the repeating arrangement of protein molecules builds up a macroscopic crystal. X-rays are then bombarded at the crystal. As they pass through the electrons within, the X-rays are diffracted. The resulting interference of these X-rays diffraction is captured as a two-dimensional diffraction pattern. From these data, we apply the Fourier transform to construct the electron density map. Finally, an atomic model is used in comparison with the density map and ultimately refined until it best matches with experimental observations. A few years after witnessing the miracle protein myoglobin, John Kendrew and Max Perutz received the Nobel Prize for Chemistry in 1962, proving that proteins exist as perfect 3D geometric structures. Though this was one great leap for men, the problem resides. Some proteins simply cannot be crystallized. Millions of proteins still buried deep in treasure chests, waiting to be discovered. If protein were to randomly sample every configuration, it would take billions upon billions of years. Yet, in reality, protein folds in just a few microseconds. This is the infamous Levinthel's paradox. First seen in 1969, it stumped the world of science. How can protein fold so precisely? Well, protein folding isn't random. Just like when light chooses the shortest path when entering another medium, protein follows nature's law of energy minimization. Here is a visual process of how protein folds. Disordered structure, long chain of amino acids, energetically unstable and structurally chaotic. Descending down the energy funnel, molecular forces, hydrogen bonds, attritions, repulsions, hydrophobic collapse, act as molecular guides steering the chain toward its native structure. Avoiding traps. Occasionally, the chain misfolds into a local energy minimum. Thermal energy provides the much-needed boost to escape. Native state. Eventually, the protein reaches its native state, the unique, lowest energy state precisely shaped to carry out the protein's biological function. The process is nature's magical optimization algorithm, a process that solves, in a blink, faster than any supercomputer could brute force. Protein folding is quite literally the origami of life. In 1971, the Protein Data Bank, PDB, was introduced, storing the first 7 structures and later expanding to 150,000 in 2019. Yet, it is only a tiny fraction compared to the amount of protein structure in the universe. Hundreds of millions of proteins await to be discovered. The PDB is more than a database. It has become the universal language of biology. From the first myoglobin model to today's most intricate enzymes, the PDB enables storage, comparison, and most importantly, connection. In 1972, the Nobel Prize in Chemistry was awarded to Christian B. Anfinsen, who posed a deceptively simple yet astounding question. How does a linear sequence of amino acids reliably fold into a functional 3-dimensional protein? This question sparks the fundamental theorem in biology, the principle of protein folding. The first step, protein selection. Anfinsen chose ribonuclease A due to its small size and well-defined enzymatic activity, an ideal candidate for protein folding test. The second step, denaturation. He denatures protein structure by using 2-mercaptoethanol, 2-ME, disrupting disulfide bridges in the process. The result? A protein without its geometric structure and function. The third step, renaturation. The protein would refold spontaneously once he removed all denaturing agents. The experiments demonstrated that all the information required for correct protein folding resides within the amino acid sequence itself. This insight is now known as Anfinsen's thermodynamic hypothesis. This discovery was foundational for modern structural biology, laying the groundwork for advances in protein engineering, biotechnology, and medicine, where understanding and manipulating folding is above all else. In 1989, the first protein structure was found by nuclear magnetic resonance, NMR. To begin with, The protein is dissolved in an aqueous buffer and placed into a powerful superconducting NMR spectrometer. Then, under a strong magnetic field, certain nuclei, hydrogen for example, emits their radio frequency. These signals are detected and analyzed to reconstruct a 3D map of the protein's structure. Although NMR is limited for larger proteins due to reduced accuracy, it is unmatched for small proteins. The process of cryo-EM goes by the following. Sample preparation. Unlike X-ray crystallography, cryo-EM requires a droplet of purified liquid protein as sample. Vitrification. The sample is placed on a copper grid, then rapidly plunged in liquid ethane, preserving their native state. Image acquisition. The samples are placed in a transmission electron microscope, TEM. The TEM flashes the sample with a beam of electrons, creating tiny clear 2D images from various angles. Image processing. A computer software is used to sort and align similar particles, which is then combined and processed into a detailed 3D density map. Finally, an atomic model is fitted to the density map. Entering the age of X-ray, NMR, and cryo-EM, humanity can finally see the protein. But actually touching the protein is still left unanswered. An astounding question remains. Does knowing the amino sequence sufficient to predict the 3D structure of protein? The answer emerged with a bold experiment, CASB, or Critical Assessment of Protein Structure Prediction. This wasn't your ordinary Joe. This was a competition, a biological World Cup, if you may. The competition strives for one thing: predict the 3D structure of protein. The rules are simple. Organizers released a sequence of amino acids of protein whose structure is already known experimentally, but yet to be published. The challenge? Competing teams are tasked with predicting the 3D fold. At the end, the experimental structures are unveiled, with the team bringing home the W as one with the highest precision. The very first CASB, held in 1994 at Alphalomar, California, carried both speculations and excitement. Could this radical idea actually work? Surprisingly, it actually succeeded. CASB1 brought together 35 research groups from around the world, bringing with them 32 structural models. Were the models great? Well, the models were crude and far from the accuracy demanded in today's standards. Yet, like a baby starting to walk, it proves one crucial point. Humanity will never give up. This marks as the first milestones of humans' attempt to solve the folding problem with pure prediction. From that moment onward, CASB became a recurring theme. Held every 2 years, it captured the minds of thousands. In 1998, at the lab of David Baker, a bold algorithm was born, Rosetta, designed to fold proteins from scratch. Its name, inspired by the Rosetta Stone, symbolized a key to deciphering the hidden language of life. Then he came up with an idea, pulling the computational power of idle computers from home, universities, and libraries, who volunteered to install his software Rosetta at home. The screensaver shows the progress of the protein folding calculation. In 2008, he launched such a game, Folded. Instead of the computer doing the twisting and arranging, humans, aka players, could, in fact, make up their own creation. We call it the grand puzzle of biology. And amazingly, in 2010, reports show that Folded players outperformed even Rosetta, proving the power of collective human intuition combined with computational algorithms. Folded offered a rare opportunity for global communities to participate directly in molecular biology research. Folded had another, less obvious, contribution. Among its players was Demis Hassabis, a name that would later make history with an invention that forever changed biology. But we'll come back to that story soon. After 20 years of trials and errors, Rosetta finally grasped the golden ticket: the residue-residue contact signals between amino acids. What were once discrete dots is now the guiding thread to unravel the mystery. The key to the breakthrough? Framework construction, using contact maps to sketch the overall topology. Refinement, polishing to atomic resolution. The results spoke for themselves. 15 out of 19 target proteins achieved a GDT-TS score above 60, proving that Rosetta could, at last, reach atomic level accuracy. Yet, CASB-11 was far from the real battlefield. The result was idealized, meaning there were abundant data and generally easier to decipher than the more noisy, complex real-life data. To truly solve the protein folding problem, scientists would have to take drastic measures, an entire new frontier, but with a twist: artificial intelligence. Hasabees had recently started his AI company, DeepMind. Their AI algorithm, AlphaGo, made headlines by defeating world champion Lee Sedol on home soil. Once a game reel folded, Hasabees continued his tale with something bigger in mind. This time, however, it is not against a human opponent, but Mother Nature herself. This was the reason for the production of AlphaFold. With AlphaFold, humanity obtained a powerful weapon: artificial intelligence, the programming language of life itself. In 2017, John M. Jumper entered the scene. Born in 1985 in the United States, he carried with him a foundation in physics, mathematics, and theoretical chemistry. But he was not just a scientist. He was the one who transformed evolutionary signals into a language that machines could understand. From that moment, AlphaFold was no longer just an algorithm. It became a tool capable of listening to life itself. And with that, it began writing an entirely new chapter in the history of science. This begs a question: how does AlphaFold 1 work? An amino acid sequence with a known structure is fed into AlphaFold 1, which searches databases, namely the protein data bank, for similar amino acid sequences and protein structures. The model focuses on two things: the distance between amino acids and their backbone torsion angles. Using these predictions, AlphaFold 1 assigns each output with a score, a way of telling which proposed 3D fold were more plausible. Using gradient descent, AlphaFold gradually optimized its models, step by step, until it arrived at a 3D structure consistent with the sequence's constraints. Then came CISP13 in 2018. DeepMind entered the stage that had long belonged to the most veteran of biologists. And the magic happened. AlphaFold 1 came out victorious, a landslide victory. It dominated, especially with the harder targets, clutching an average GDT-TS score of approximately 58. A truly miracle run, just like what Portal did in the Champions League back in 2004. From the unknown to the champion of the world, AlphaFold 1 had achieved the unthinkable. If Rosetta was the explorer with a flickering lantern, shining the way for biological advancement, then AlphaFold 1 was the destroyer, ripping the boundary of human imagination. A new dawn waiting to be discovered. Truly, an extraordinary sight. In 2020, the problem has been solved. CASB13 was just the beginning. 2 years later, at CASB14, AlphaFold 2 was introduced and, again, shocked the whole world. Its accuracy rivals that of experimental methods, such as X-ray crystallography and cryo-EM. So, how does AlphaFold 2 work? The system begins with an amino acid sequence. To provide evolutionary context, it constructs a multiple sequence alignment, MSA, from homologous sequences and retrieves structural templates from the protein data bank, PDB. Output: a preliminary representation consisting of the MSA features and pair representation. Attention is applied in the MSA when the EVO former finds two closely related linked amino acids, which means that they are important to evolution. Then they are transferred to the pair representation, which uses triangular attention to calculate distances between amino acids. If the pair representations find that it's geometrically impossible for two amino acids to be close to each other, it tells the MSA to ignore their relationship. This exchange goes on for 48 times, refining and tuning until they are passed on to AlphaFold 2's structure module. The structure module outputs a 3D protein. In the 2020 CASB14, AlphaFold 2's team rose above all, but this time with historical feats. They reached the gold standard of 90. AlphaFold's prediction was literally indistinguishable from experimental tests, something once thought as impossible. But why stop at competition? DeepMind decided to take a step further. In the midst of the epidemic in 2020, DeepMind unleashed AlphaFold into the fight. They published the structural predictions for several SARS-CoV-2 proteins, including AuraF3A, NSB4, and NSB6. These are proteins notoriously difficult to be laboratory tested, but unexpectedly, they were all in the margin of acceptability. This was the first real-world demonstration that artificial intelligence could contribute immediately during a global health crisis, contributing to the production of medicine and vaccines. By the end of 2020, AlphaFold 2 has stunned the scientific world many times. But as the shockwaves settled, a new question arose. Could the power of AI be shared openly, rather than remaining in the hands of a few corporate giants? The answer came in 2021 from the laboratory of David Baker at the University of Washington. His team unveiled RosettaFold, a completely new artificial intelligence system allowing amino acid sequences and 3D spatial coordinates to communicate. The magic doesn't lie in precision, but in speed and accessibility. Once a daunting task, taking hours on end in laboratories, now could be done in mere minutes on quite literally a video game console. This reflects what Baker once said. With RosettaFold, a protein structure can be computed in as little as 10 minutes on a single gaming computer. What does this mean? It means that from now on, every laboratory, every facility, or even the person sitting next to you, or even you, could access the most advanced technology with no restrictions or subscriptions. RosettaFold was released publicly, empowering thousands of scientists to explore proteins, accelerating drug discovery, vaccine development, and even synthetic protein. The following years marked the dawn of a booming era, where AI reshaped the frontiers of scientific discovery. 2021, DeepMind released the first AlphaFold protein structure database, containing about 350,000 3D protein structures, including the entire human proteome. It was the most detailed map of human proteins ever assembled. Just a year later, AlphaFold expanded exponentially. Over 200 million structures, covering nearly all of protein known to science. Headlines around the world capture the moment. AI draws the map of life. May 2024, DeepMind introduced AlphaFold 3, extending its predictive power beyond proteins to DNA, RNA, and even small molecules, modeling interactions at near atomic resolution. October 2024, Demis Hassabis, John Jumper, and David Baker were awarded the Nobel Prize. The honor recognized not only three brilliant minds, but also artificial intelligence itself. Now acknowledged as a new instrument of science, artificial intelligence has opened the world beyond the realm of impossibility. After decades of breakthroughs, biology has finally ripened enough for a daring idea. What if we create a never-before-seen protein de novo? It begins with setting a goal, a stable alpha helix or beta sheet framework, or a motif tailored for a specific task. Next, create the structure foundation with the help of RosettaFold and RF diffusion. Then sequence design takes place, assigning amino acids to each position so the chain naturally folds into the intended structure. This is called inverse folding. Finally, AlphaFold steps in as the quality inspector testing whether the sequence will fold. This filter provided a 10-fold increase in experimental success rates for de novo binder design. Step 1. Write the code. Scientists turn amino acid sequences into synthetic genes. Step 2. Run E. coli. The genes are put into E. coli, which then manufactures the designed proteins. Step 3. Match the structure. The proteins are captured and imaged with cryo-EM, then compared against AI models. If the structures match, their functions, binding, catalysis, and so on, are tested. And finally comes the cycle of refinement. The most promising designs are kept and improved, while the rest are fed back into the loop for another round. At last, the fruits of humanity's hard work. In 2016, scientists built self-assembling nanomaterials from roughly 120 protein units with an angstrom precision. By 2021, a nanoparticle mimicking influenza proved to be a valuable vaccine candidate that showed protective effects in animal trials. In 2022, a de novo enzyme capable of breaking down plastic was created, offering a green path to recycling. And between 2021 and 2025, the cancer drug candidate LL201 made its remarkable journey, from an idea tested on Rosetta at-home screens all the way to phase 1 clinical trials. A new chapter unfolds. If a single protein correctly folded was the breakthrough for the 75 years long mystery, imagine what every new discoveries would change. A doorway to heaven, a new dawn, an uncharted world awaits. And now, for the first time, humans are not alone. Side by side with artificial intelligence, we are no longer confined by the means of our body, by evolution, by Mother Nature. A revolution where intelligence, both artificial and biological, unites to conquer of what once thought is impossibility. And in that union lies a promise, the code of life, once a mystery, has now been deciphered.